speed of light, 3 times 10 to the 8th meters per second. And it's basically the speed of every single electromagnetic wave is 3 times 10 to the 8th meters per second. So what is an electromagnetic wave? Well, your cell phone uses radio waves. Those are electromagnetic waves. Your cell phone also uses microwaves. Those are also electromagnetic waves. If you've ever gone to the dentist and gotten an x-ray, those travel at the speed of light. If you've ever gotten a sunburn, that's UV light. That goes at the speed of light. Visible light, the stuff you see, that goes at the speed of light. All those are examples of electromagnetic radiation. Look here for a second, though. This is the speed of light and the radio waves and all those other things I just mentioned. This is the speed of sound, 1,000,000 times different. So when you're in your car and you turn on the radio because you don't have anything else to listen to in your car for some reason, realize that the radio station in Poughkeepsie or Middletown is not broadcasting that signal at the speed of sound. If it were, you would, when the guy said, oh, it's 10 o'clock, you'd probably hear it at like 10:30 or 11 o'clock or something, depending on how far away you were. But if he says that and it gets to you by radio waves, which is how it gets to you, it's going the speed of light, and it gets to you almost instantly. The speed of light, if you calculate it, how long it takes to go around the world, it's on the order of a second to go around the whole circumference of the world. So it's very, very fast compared to sound. All right. The index of refraction, this n, which is just a value we're going to give to different materials, can be thought of as a slowdown factor, meaning the bigger the n is, the slower light is going to travel, or electromagnetic radiation is going to travel through this new material. So the bigger the n, the slower it goes. So I want you to look right here just for a second. So down here we have the absolute indices of refraction. So this is the index of refraction. And you notice air and vacuum is 1. And corn oil is greater than 1, and therefore it goes slower. If you look at these, you can see the fastest thing is air. And out of all these, the slowest thing is diamond. And actually, this is why diamond makes such a beautiful stone when you cut it properly. And it's because white light is made up of different colors of light. And the different colors slow down different amounts. And therefore, when you have a diamond and the light starts to reflect around inside the diamond, the blue separates from the red, separates from the yellow, and you get the sparkling effect when you look at the diamond in the light. And the sparkliness comes as a direct result of its index of refraction. One thing to note, there are materials with higher indices of refraction. Here you have zircon down here, which is really close, but zirconium, which is what they make fake diamonds out of, actually are more sparkly than diamonds. It's one way people can tell a fake diamond. If it's super sparkly, it's because it's actually made out of zirconium, which, by the way, diamonds are a horrible investment. You should never want a diamond. There's nothing wrong with zirconium. But anyway, look up here. This frequency, these slowdown factors are only true at this frequency. Now, we're only going to use these numbers. We're not going to look up other indices of refraction, although we could. But I want you to look at this, 5.09 times 10 to the 14th hertz. Now, this frequency, look up here. These are all the electromagnetic waves that we know about. Radio waves, TV waves, microwaves, infrared. I'm going to skip over this for a second. Ultraviolet, X-rays, and gamma rays. Now, gamma rays, X-rays, and UV are what we call ionizing radiation, a little bit dangerous. And visible light is this tiny little piece in here. Actually, it's way smaller than this even. But this tiny little piece in here that is all our eyes can see. So our eyes can only see this part of the electromagnetic spectrum. Now, we have different animals that can see ultraviolet and different animals that can see infrared. Snakes, for example, can see at night and infrared. Bees and birds, for example, can see ultraviolet. And our eyes are just like our ears. Our eyes are also frequency detectors because that's what we're detecting are different frequencies. And I want you to look at this frequency right here, 5.09 times 10 to the 14th hertz. Look at this. All of these visible lights are 10 to the 14th, 10 to the 14th, 10 to the 14th, and they range from 3.8 to 7.69. And this 5.09, it's right here. It's yellow light. It's kind of in the middle. So all these indices of refraction we can actually use as approximations for all these colors, but they actually all have slightly different indices of refraction because these things go different speeds in the different materials. Okay, well, in the same material. So in like diamond, the red and the violet go different speeds. Okay, all right. So
Excuse me.
yes, go ahead.
So I've picked up 2 facts regarding light. It's pretty interesting.
Okay.
First one being, if you had a strip of paper as long as the United States, end to end, California to the colonies, you would get. So if you laid it across the nation and you printed on it every single wavelength of light that we know about, visible radiation would actually be 100 nanometers in the center.
Yeah, so what you're saying is that this is way, way, way too big, which is correct.
Yeah.
This is what we call a logarithmic scale here, and so this is really just so you can see that the part of this scale is actually visible light.
Yeah.
So, no, that's true.
And then what?
Go ahead.
Yeah, and then the other interesting thing I picked up is that there was this artist who always went to the same place to paint the same bridge. Every painting was of that bridge, but he did that so that he could document how his cataracts were affecting his vision. But then he got a surgery, an experimental surgery in that age, which removed the lenses of his eyes, and he was able to see a little bit into the infrared spectrum. Not infrared, sorry. A little bit into the ultraviolet spectrum.
Interesting.
It actually appears that the lenses of our eyes, the lenses of our eyes absorb that radiation.
Well, that sort of makes sense. Glass, for example, is extraordinarily effective at absorbing UV. So if you're driving in the car on a sunny day with the windows up, you're not going to get a sunburn. But if you have the windows down and you have your arm out of the car, you're going to get a sunburn on that arm because the light is, the UV is absorbed by glass very effectively. All right, so let me keep going here, but you did bring up something I wanted, or you reminded me I wanted to say one thing. All of these things have one thing in common. They all travel the same speed in a vacuum and in air. And the difference is that they all have different frequencies. And so, for example, radio waves has a relatively low frequency relative to gamma rays, but the wavelengths are inversely proportional, right? Because V equals F lambda, and V is constant. So when F goes up, lambda has to go down. And when F goes down, lambda has to go up. So here we have our big wavelengths and our small wavelengths. And here we have our high frequencies, and here we have our low frequencies. So these guys, they're all electromagnetic radiation. We collectively refer to all of these things as light because they all travel the speed of light, but they're better known, or they're more correctly called electromagnetic radiation because they all work the exact same way. The only difference is how fast the electrons are, whatever's creating this wave is accelerated, which creates the frequency. The vibration of the disturbance is the frequency of the wave. Okay, so try this one real quick. What's the speed of light in a medium with an index of refraction of 2? So now we know the speed of light is not the speed of light that we know because it's asking for the speed of light in a medium. But we do still know the speed of light. So we write down the equation N equals C over V.